Good evening. My name is Torolv Röberg, and today I'm going to perform a miracle. The date is 2nd of July 2022. I am going to do what Albert Einstein and Stephen Hawking dreamed to do but were not able to. I am going to unify quantum mechanics and general relativity. But before I do that, I would like to remind you of a story in the Bible, which is David versus Goliath. Because this task is over 100 years old. It's kind of the task for scientists. And I'm going to do it. Let's go. Okay, so the marriage of quantum physics and general relativity. And I'm using a manuscript because there's a lot going on in here and I need it concretized. Let's begin. As Einstein established in 1905, E equals mc squared. This, in essence, means that matter and energy is the same. Throughout my hypothesis, I will be referring to both normal energy and matter and dark energy and matter when they are in the same sentence as just normal or dark mass. The essence is that dark mass has a quality called anti-gravity. That means that instead of pulling towards, like normal gravity does, it repulses and pushes everything away from itself. The universe is expanding. This is the consensus in the scientific field today, and it is correct. Not only is it expanding, but it is also accelerating. This is because it has the opposite effect of normal mass. The closer we are to normal mass, the stronger the gravitational pulls you in towards it. And the opposite, the further away you are. So the closer you are, the stronger the force. The further away, the weaker the force. On the other hand, the further away you are from dark mass, the harder it pushes you away. And again, the opposite, the closer you are. What we believe about dark mass today is that it makes up about 95% of all the things or stuff in the universe. And this is plain wrong. It's probably closer to about 99.999 etc. percent of all the things in the universe. And a rough estimate is that about 80% is dark matter. That's my estimations, and probably way wrong. I refuse to do the math, I just like to think. And this is because the scientists didn't even consider the possibility that it might have the quality of anti-gravity. I had a friend who helped me with the maths in the case that dark mass has anti-gravity, and it does not fit with my thinking. So that's why it's not 95%, but because then the universe would be mostly empty, and it is not empty. So this is an invitation for you, mathematicians, physicians, astrophysicists, whatever. Go get your Nobel Prize, because I really don't want to bother with it. So, an atom can get filled with dark energy, and when it condenses, it loses a lot of power and is converted into dark matter because it is not free to expand anymore. It's not energetic as it used to be. It's limited now. Einstein claimed again that E equals mc squared, which basically means that matter and energy is the same. And with dark matter, it's very clear to see, because the only thing that differentiates dark energy and dark matter is that dark energy is not bound up by normal matter and its gravity and can expand freely. The atoms get filled up with dark matter and can no longer hold anymore. So I'll come with an example soon. This makes the excess dark energy in its vicinity free to repulse away from the bondage of the gravity that is given through the normal matter. So now we've established how dark matter and matter works in general. Now let's take a look at the quantum level. Protons, neutrons, and electrons are the building blocks of all normal matter in the universe. It's got mass and is therefore and also has a gravitational field. This includes the electrons, which we consider to be just energy. Now, the gravitational field to normal mass is a lot stronger than the anti-gravitational field to dark matter and mass. Though the further away from the core of the atoms you get, the stronger the anti-gravity becomes. As we can see in my drawing here, is a poor attempt of a drawing of a hydrogen atom. The dot in the center is the proton, and the cute little dot down here is the electron. The horizontal and vertical lines represent the gravity of the normal mass, which is the proton and the electron, whereas the diagonal lines represent anti-gravity of dark mass that repulses everything away from itself. Now, this is what makes atoms stable. The forces of the gravity of the matter itself and the anti-gravity that compresses the matter from the outside. So protons don't repulse each other, because this has a lot of force even though it's weak. So it's kind of paradoxical. So the protons, they want to get away from each other because they are both positive. But it doesn't let it, because all the mass it has to pass through is too much for it. So it sticks together, and this is the strong nuclear force. Now, that I think should do the basic principle for the quantum level. Now let's look at how antimatter works on the great scale of things. The reason dark energy and dark matter is theorized is because galaxies apparently don't have enough mass to keep itself from dismantling itself, just shooting away in all directions. Therefore, scientists have come up with the term dark energy and dark matter, although they made one mistake. They gave them the same properties as what we call normal matter and energy. And just like the atmosphere on the Earth is denser at the surface level of the sea and gets less and less dense the higher up you move in the atmosphere, the same principle applies with antimatter, with planets, stars, and galaxies. This is the reason there is a curvature in space-time. If you take a look at my second drawing here, you'll see why. If there was only gravity, there would be no smooth transition between gravity points of multiple places in the universe. And it would look like this. There's nothing that holds it against itself. It's just gravity pulling everything down. Whereas with anti-gravity, it balances out the forces that makes a field that stabilizes itself. So this is the correct one, right? And because if there was only gravity, like this, the universe would not be able to expand, which it does, and especially not accelerate, which it also does. Rather, it would be like this, pulling everything into the heaviest objects in the universe. The same model can be used for our solar system as with the electrons and the protons. As you see here, this is a poor attempt. Again, keep in mind that this is a 2D, almost one-dimensional representation of a 3D concept, so it gets massively distorted. And but the principle is that the sun pulls and has a field of antimatter that pushes away slowly, and it meets with the Earth's, if this is the Earth's gravity and anti-gravity, so it balances out. So if the Earth was a couple kilometers closer to the sun, this balance might not be as good, and we would fall into the sun, because then anti-gravity would be weaker and gravity would be stronger. So the sun would pull the Earth in, and eventually, if it didn't pick up the speed in order to keep orbiting, then it would just go right in. So yeah, that's the solar system. And now let's see. Yeah, this is a picture that I drew myself of how gravitational waves look like. Oh, not gravitational waves, but how the gravitational field looks like in a two-dimensional place. The closer you are the object, the more it's pulled towards that. Whereas you have one place, it should be a circle actually, but I made a square because I like squares. There's a place where you can just stand still, where you won't get pushed away or pulled in. And outside of that place, there is anti-gravity. So slowly you will begin to get pushed away, and the further away you get pushed, the faster you will get pushed away. And this is when we come to galaxies. Again, horizontal and vertical lines are gravity, and you see them, they're strong closer and they get weaker and weaker, whereas anti-gravity gets weaker, starts weak and gets stronger and stronger and stronger. And here is a representation of how it looks. It's very dense with antimatter near and inside the galaxy, and as you move further and further away, they get less and less dense, more spread out. However, this means that they're more powerful as well, because they are free to expand faster and push everything away, and this is what drives the expansion of the universe. So here is how a representation of how antimatter works. Whereas gravity would pull everything together, antimatter is pushing everything away from itself. Here is a picture of two galaxies. The outer border here is the border where gravity stops being the dominant force that affects the gravity. So if you are here, you're going to move towards, you're going to fall into the galaxy. Whereas if you're outside, you're gonna get pushed away. And these small dots here are supposed to represent the antimatter. That's very far apart. And the further away you are, the fewer the particles will be. So in the middle of nowhere, right here, there should be very few of these. And because they're pulled apart so fast, that's what creates the redshift in the light when it emits from the galaxies and trying to reach, because of the expansion of the universe. And this is the leading force of that. So, how does this work with black holes? Well, black holes are so dense that they don't even let light escape their mighty gravity. This is wrong. It's wrong, and I'll show you. Okay, so I agree that a black hole has a lot of mass. And that means as normal mass is stronger than anti-mass, it's going to attract a lot more antimatter or anti-mass and create antimatter. However, it's not the gravity that affects light. It's the antimatter. Because the antimatter is being layered upon the singularity. Just like with the atmosphere of the Earth, it's getting weaker and weaker the higher you go. The same principle applies here. So light isn't affected by gravity, but it's affected by the matter or antimatter it goes through. And I'll show you an example. This glass of water, it's a different material, the water, than the air. And this is why there is a bending in the light. So it's distorted because of there's a density. So it changes speed in other substances. And this is why when it first enters, they have an event horizon. If it doesn't hit there, then it will not be able to escape. But here, it's able to escape because it accesses or it enters the antimatter field. That's the upper limit or something like that, and then it goes down, slows down, and then it goes around the black hole, or not around it, but just barely misses the event horizon, and then it hits something that goes faster, and then it goes out again, though not in the same direction as it was supposed to. Whereas if light comes in at an angle and it hits the event horizon, then there's no return, because all the gradients of the stuff just drags it further down. And to further explain this, I've heard an example which is quite nice. That is with a race car. It starts on an asphalt road, and then it goes to a road that's not as good, or it's slower, or just more sticky, and then more and more sticky. And as the first wheel hits this this slow substance or road, then that wheel is going to be slower than the one on the outside, and that's going to be faster. So it's going to be like this, and that's gonna keep doing that until it eventually goes in a straight line this way, and that's the center of the black hole. And that's what the light cannot escape. So light does not interact with gravity at all, but it reacts with the matter, which is dark matter. And this is because of the gravity that attracted the dark matter. And last but not least, as a final blow from me to legitimize this hypothesis, it also explains gravitational waves. When two black holes spin around each other, they create gravitational waves. Dark energy is what these waves travel through. As the black holes move with such a speed, often close or a fraction of the speed of light, and is so dense and massive, and the dark matter is so tightly packed around it, it bumps into it bumps into these antimatter particles that are everywhere and create a dark or a spiral in the dark matter, which are waves, because the antimatter is trying to keep up with it, but it's going so fast and it does not expand here. So that makes it go outside, and it bumps into other particles that are trying to push themselves away. So every push, and then it pushes, and then it hits something in the back, and then it goes right back again, and it's wavy. And yeah, that's the marriage of quantum mechanics and general relativity. Thank you for watching. I've been Torald Röberg, and I'll see you soon.